In a previous lesson, we already talked about coherent and incoherent beams of light. Aside from some lasers, it's barely impossible to get two sources of light that are coherent. Sources are not perfectly monochromatic, and the time average of delta, the phase difference between two beams of light we derived in the previous lesson, is going to be zero. That is, the phase difference is going to randomly change. So, for two mutually incoherent beams of light, we will have that I is equals to I1 plus I2. What if we have two mutually coherent beams of light? We can accomplish this by splitting the beam from a laser source and making both beams recombine later. For example, using a Michelson interferometer, of which we will talk about later in this chapter. The phase difference delta can be written as ks2 minus ks1 plus phi2 of time minus phi1 of time, where phi is the change in phase due to time and s is the path traveled. In this case, whatever the phase of one of the beam experiences, the same will experience the other beam of light. So, if we make both paths of equal time, phi2 minus phi1 is going to be zero. Well, the expression for the interference term is the one we derived in the previous lesson without the average. The irradiance at interference is the irradiance of beam 1 plus the irradiance of beam 2 plus 2 times the square root of irradiance 1 times irradiance 2 times the cosine of the phase difference between both beams at the point of interference. We define the coherence time as the time interval over which there is no significant deviation from monochromaticity. It is a time measure of coherence interference. Of course, if we had a perfectly monochromatic beam, that would require an infinitely long wave, and coherence time would be infinite. If we have a short pulse of light, we actually have a superposition of several wavelengths, and we'd have a very short coherence time. This coherence time is proportional to 1 over delta nu, where delta nu is the range of frequencies of that pulse of light. Remember that if you don't have an infinite beam of light, you're going to have a pulse of light, longer or shorter. Correspondingly, we define coherence length as the length traveled by light during that coherence time. And this indicates the size of the experiment which we can do if we aim at coherence interference. You always want to be in the coherence length, for which lasers can range from some centimeters to some kilometers. When you do an experiment and observe the interference pattern on a screen, because each point on the screen means a different path length for each of the beams, you will observe bright and dark areas on the screen. You will observe interference fringes. Cosine of delta ranges from -1 to +1. Let's think of the experiment where you have one laser, you split the beam into two beams, you make them interfere then, and you observe the interference pattern on the screen. Assume you use a 50-50 beam splitter that splits the beam into two beams with the same intensity. So I is equals to 2 I naught times 1 plus the cosine of delta. This can go from 0 to 4 I0. So we can have constructive and totally destructive interference on the screen. Of course, if both beams are not identical, there will always be some remaining light in the case of destructive interference. That is why it is important to define visibility of the interference, which measures the fringe contrast. Visibility equal to Imax minus I minimum over Imax plus I minimum. This is a number that can range from 0 to 1. Making the visibility as close to 1 is very important in many experiments to reduce uncertainty in your results. This video here is of the visibility of an interference experiment. The oscillation is because one of the mirrors was attached to a piezoelectric device. A piezoelectric device is made of a material that when receives an electric voltage, it expands. When attached to the mirror, you can change the position of that mirror by a small amount. To check the visibility, you can make the mirror oscillate and then obtain this sinusoidal pattern from where you can measure Imax and I minimum and then calculate the visibility out of them. This particular experiment involved interference of single photons, so we had to work hard to get a visibility as close to 1 as possible. Of course, the signal you see here is not with single photons, it is with a beam of light from the laser that I would use later for the actual experiment. For that experiment, I would then attenuate the laser to the single photon level. This was just a measure for calibration of the setup. For this particular experiment, I could get a visibility of 0.995. Have a good visibility, and may science be with you.